I gave you a sneak preview of a couple of things that we are going to dive into a little bit more this week. One of those things was the idea of conservation of momentum, the idea that momentum in certain circumstances can be conserved. So what we talked about is that if we think about a system of interacting objects and we know the momentum of all of those things, we can find it, we know how to find it, it's the object's mass, which we can measure with a balance, times its velocity. We have a bunch of ways of measuring velocity, you'll use at least one of those today. So we can find momentum of any object. If we think about what's going on in this situation, and we can kind of rule out a couple of possibilities of how things could get tipped out of equilibrium, then we can determine whether or not we can apply the law of conservation of momentum, and we can use some math to make a bunch of predictions, right? So our goal today, we're gonna kind of extend this over a couple of days. Our goal today is just to be able to find the momentum of objects before and after a collision. We can use that to evaluate whether or not momentum is conserved within that system over some period of time. The law of conservation of momentum basically says that, like, throughout the entire universe, anytime we have an isolated system, the total momentum of all the objects in that system combined will stay the same. So you can write this down, or you can write down what I said. The law of conservation of momentum is pretty simple to state. The total momentum of an isolated system never changes. The universe itself is an isolated system. So if we were to look at the momentum of every single object and particle in the universe at this moment, it will always be the same. In 12 billion years, the momentum in this universe, everything added together, will be the same. It always was the same, it always will be the same. In practice, we work with systems that involve objects that we can actually, like, relatively easily find momentum, whether it's by using mass and velocity or by using some other mechanisms, but we can find the momentum of objects. And what we do is we play a couple of little tricks, and we'll talk about some of those little tricks today, and we'll talk about some of those little tricks afterward. And mathematically, it looks like this. This is our this is momentum. Sum of momentum, 0 means initial, is equal to sum of momentum, F equals final. And I'll show you another version of this, so you don't have to write that down right now. The most important thing for you to kind of picture right now is the idea that momentum in an isolated system is always the same. You add up all the momentum, all the objects, it's always the same. So what does that mean? Well, first of all, there's some implications here. The simplest case to think of when we have a system is 2 objects. Okay? One object is technically a system as well, but it doesn't interact with anything, so it's not that interesting. But if we have 2 objects, which is primarily what we're going to be working with, then if momentum is conserved, then we can look at changes in the momentum of each object, and what we'll see is they kind of balance each other out. So if one object increases in positive momentum, the other object will increase in negative momentum, and vice versa. The change in momentum of one object will always be the same as the change in momentum of the other object, but in the opposite direction. So we can make some predictions based on that. That's something that we saw mathematically when we were looking at the virtual cart activity. One of the columns that I had on my spreadsheet that I asked you all to think about was, what is the change in momentum of ball 1 compared to the change in momentum of ball 2? And the answer was, they're almost exactly the same magnitude, and they have the opposite sign. And when we think about momentum gained and lost, it gets a little tricky, because part of the time when we're thinking about momentum, we really only care about magnitude. So if you look at 2 motionless objects. The magnitude of each of those objects' momentum is 0. It's not very hard to stop either one of those objects. They have no momentum. But if two objects with the exact same mass are moving toward each other with the exact same velocity, the total momentum of that system is also 0. The momenta is in opposite directions, so the total momentum is 0. But that feels really different because we know one cart is going to be hard to stop. The other cart is going to be hard to stop as well. So when we think about momentum, we think about how hard something is to stop, and we think about the direction in which we would need to push to stop it. And as you'll see, it gets a little tricky when we start thinking about positive and negative momentum, because negative momentum is just as difficult to stop as positive momentum. All positive or negative tells us is the sign. What we really get from the sign is how hard it would be to stop something by pushing in a certain direction. If something has negative momentum, which might be this way, then it's going to be really, 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 really difficult to stop it by pushing in that same direction, as in impossible. Whereas if something has positive momentum and you push it in the negative direction, you can stop it. Theoretically, you can stop it. If it's really massive and moving really fast, then you personally aren't going to be able to stop it. But if it's a grocery cart with some frozen pizzas in it, you can stop it. If you try to stop that grocery cart with frozen pizzas by pushing in the same direction it's moving, you're out of luck. So there's negative momentum, positive momentum. They're both how hard something is to stop, but the direction matters. So when momentum is exchanged, something might become easier to stop by pushing on it this way, and harder to stop by pushing on it this way. So you can gain positive or negative momentum. And then one thing that we like to use a lot when we talk about momentum as an analogy is money. And the big problem with money is the negative, because money doesn't have a direction. When we talk about positive money, we're talking about like money. When we talk about negative money, we're talking about money that don't have. That's not how momentum works. Momentum isn't positive if you have some and negative if you don't. It's positive if you have some in one direction and negative if you have some in the opposite direction. So be aware, the sign analogy breaks down here. But if we think about objects with only positive momentum, then we can imagine money as a great analogy for conservation of momentum. So let's say that Nick and I both have $100. I don't have $100. He probably does, but I don't. But let's say that he does. And that means together we have $200. Now over time, the amount of money each of us has might change, because we can like give it to people, we could buy things and sell things. But if Nick and I are the only people in our system, and we have some candy and some Legos and some other interesting knickknacks that we'd like to buy, like tennis balls and like metal bars, well, we could potentially exchange money for goods and services, as Homer Simpson would say. So that means I could give Nick $10 and he could give me a tennis ball. And then he gave me $4 and I gave him a Lego or an apple. And if we were to look at how much money Nick has over time, we'd see it goes up and down. If we were to look at how much money I have over time, we'd see it goes up and down. But overall, we'd still have $200 always. If I give him $10, his amount of money increased by 10, positive 10. My amount of money decreased by 10, negative 10. The total change overall was 0. He went up plus 10, I went down minus 10. The sum of those two things is 0, which is the overall change in momentum of the system. So when we have isolation, money is conserved. When we have isolation in a system, momentum is conserved. What does that mean? That means what can change momentum is external forces. If we don't have any external forces in a system, then we consider momentum to be conserved. If we extend the analogy to the money analogy, then an external agent might be another person or a bank or something like that. So if we were to look at the amount of money that Nick and I have, if it's $200 to start with, and then like 20 minutes later, between the two of us, we only have $170. That means $30 went somewhere. Maybe one of us bought a really cool aluminum cart from somebody who was walking, down the breezeway. If we ended up with $260, then maybe somebody came and bought something from us, like this awesome aluminum cart. And that kind of input or output from the system means it's not in isolation. The same thing happens with momentum. In the case of momentum, what causes a system to not be isolated is the presence of forces from other objects that are in the dimension of the collision. So if we have two objects that are moving toward each other, or they collide as they're moving in the same direction, there's a one-dimensional aspect to the collision itself. And if something else is pushing or pulling on one or both of those carts and creating an overall unbalanced force in that same dimension, our system isn't isolated. A really simple way to illustrate that is by taking these two carts and showing how well, if they're rolling toward each other and they collide and bounce off each other, if we think about what are the forces acting in the direction of that collision, it's only the carts themselves. Now, I had to push them to get them started. So as long as my hands are on them, I am applying an external force to each cart in the dimension of the collision. Momentum is not being conserved. But as soon as I let go, momentum is largely conserved. One of the things that we're seeing here, though, is that they slow down and they stop. Friction is a force that's opposing the motion of each cart. That's in the direction of the collision. Friction sucks momentum out of the system. Friction is generally considered to be an external force, and I'll tell you in a second how we deal with that. We have a really simple trick for dealing with friction. Here's an example of the same system, only there is an external force in the direction of the collision. Okay, if I tilt my ramp, now there is a component of the gravitational force acting in the dimension of the collision, and momentum is no longer conserved. Neither car was moving at first. There was no momentum at all. They both gained momentum in this direction as they rolled. The total momentum of my cart system was increasing over time. Why? Because there was an external force on both of those carts in the direction of where they eventually collided. Believe it or not, we can often deal with that too, using essentially the same trick that I'm going to show you in just a minute. So what we're going to think about is collisions between two moving objects in general, in which momentum is conserved pretty much right around the collision. And I'll show you momentarily how we're going to deal with that. One example of conservation of momentum is this Newton's cradle. You guys have all seen. These are like, in the 80s, all the executives had these on their desks, but now I don't know that anybody even has desks anymore, so you probably see these like in a Zoom video. But this kind of a system here is a great example of conservation of momentum. It's also, interestingly, a great example of when momentum isn't conserved. We're not going to talk about that part. We're going to talk about the part where momentum is conserved. Later, we'll hit why momentum ultimately is not conserved in this system. If you think about what's happening right as one of these balls comes into contact with the other two, it's moving in this direction. There's not much friction acting in the direction of that ball. There's no part of the gravitational force that's completely sideways, which means this is an isolated system at the moment of the collision. That means momentum should be conserved. What we should see is however much momentum this ball has right before it collides with the other two, this ball will have right after the collision. And that's why we see this predictable pattern. If you take one ball and let go, then one on the other side will move. But if we take two, and this one isn't super well made, but you can see we have to have the same amount of momentum before and after the collision, since momentum is conserved right around the collision. Now, some of you are going to think about that and figure out why ultimately momentum is not being conserved here. Not within this system, but in the moment, right before and after the collision, it is. This is the equation that we're going to use, and we're going to come back to this tomorrow, because you can write this down now, but this is really what's important. The sum of momentum before a collision is the same as sum of momentum after a collision in any system that's isolated. When I say collision, what I'm really implying is interaction, force between. We're going to think about it in terms of collisions because that's the easiest thing for us to model. But there are other ways that we can think about collisions that are a little odd, like this, for example. If we have two carts sitting next to each other, and they're just next to each other, they're touching each other, and then all of a sudden there's a force between them, that's a collision in physics, because there's a force between them. So we'll talk about that in just a moment. When we think about this in terms of two objects moving one-dimensionally, we arrive at something that's relatively straightforward, which is if we know the mass and velocity of one object before the collision, mass and velocity of the other object before the collision, the mass and velocity of one of the objects after the collision, we can make a pretty easy prediction about, say, the velocity of the second object after the collision. We'll show you the algebra tomorrow. For today, just understand that these are all variables that we can measure. So if we know enough of them, we can find unknown information. We could find how fast something was going before the collision if we have all the other measurements. We could find the mass of an object if we observe enough velocities. So any single variable in here can be solved for algebraically, which means all we need to do is measure everything else and we're good. What we're going to be doing over the next couple of days is trying to figure out a mass. We're going to try to figure out an unknown mass. For today, we're going to start simple, so we'll come back to this tomorrow. I showed you a weird example of a collision, and I want you to think about this. I can't, these poor cards are so old. I want you to think about this and extend it to an explosion like fireworks where we've got 2 and 3 dimensions. Okay, so in a one-dimensional explosion, kind of looks like this. A 2-dimensional explosion would involve movement along 2 axes. That might be something like if you had a spring set up in the middle of a bunch of like pool balls, and all of a sudden it went off, and they all went flying off, but none of them were going up or down from the table. A 3-dimensional explosion looks like this. Take like a minute and tell me what you think about whether or not momentum would be conserved given what you know now about conservation of momentum. Okay, go.
I think
What do you need to know? What's the one criteria for no external force? So ask yourself questions like, is there an external force with the fireworks? Is there an external force with my carts?
fire causes explosion.
The fireworks conservators
Okay, so let me hear what you think. And one thing to add to this is the spring, right? Like, so how many of you think about, well, the spring is sort of external? Does the spring feel internal or external?
Yes.
It's a little weird, huh? But here's a way that you can think about it. If I have these two carts and I roll them toward each other, we would think about this as an isolated system. There's no external forces involved. The force is all about the carts pushing on each other. That's really no different from the situation that I showed you where it starts with the spring squished. It's still force from one cart to the other cart. Yeah, the spring is involved, definitely involved. But it's not really any more involved than it is when they just bounce off each other like this. So we can consider this case an isolated system. So in this one-dimensional explosion, you think momentum is conserved? Wyatt, what do you think?
I said yes.
Why?
Well, I wasn't thinking about a one-dimensional one.
Yeah. Oh, you were thinking about this one?
Yeah.
Okay, you think momentum is conserved here, why?
Well, like in a bomb, like
Yeah.
I was thinking about the shock wave.
Yeah.
Like after it explodes,
Yeah.
all the momentum is super concentrated and super high, but as it like expands, the momentum goes to the air, and like as it goes out, all the momentum is there. It's just more spread out into the air.
Yeah, so first of all, yes, you're right. Second of all, where things get really complicated with a system like this is when we try to think about it happening over a long period of time. It ends up that, yeah, momentum is conserved if we consider the air particles, and actually there's one other thing going on here that's really a complicating factor. If you think about the air particles that could potentially be collided with, like there's momentum there too. We can't see them, but they're moving. There's another piece here, which is there's an overall external force downward on the particles from these fireworks. That's why eventually they all acquire downward momentum. They didn't necessarily start with that. Some of them started with 100% upward momentum, but eventually they go back down. Those are external forces. How do we deal with that though? What we're gonna do to deal with it is we're gonna narrow our time frame. It takes time for gravity to change the motion of an object. It takes time for these individual firework particles to interact with particles of air. So if we just look at a really, really, really narrow time frame, right before and right after a collision, then we can almost always assume that momentum is at least largely conserved. In our cart system, we're gonna do the same thing. In general, as long as we don't have the cart or have the track like terrifically slanted, if we look at momentum right before and right after a collision, we can assume that it's going to be conserved. And it really is. I mean, mathematically, as you'll see, it is generally really close to being conserved. So here's your task for today. I have what I consider to be a stunningly produced video. This is a video that I made with, I don't remember who, maybe some biology students a couple weeks ago. And it's really fantastic. Look at that action. This, I think, could probably win some awards. Here's what I want you to do. I want you to use this video, which is posted to Canvas, and I want you to find 4 velocities. And I want you to check with other people. You can work in pairs or threes to find the velocities, but then check with other people as well. There's a couple little tricky things about this. The first tricky thing is how do you make measurements? Like we can see where it is, so measuring distance is pretty easy, but what about time? Well, it turns out that if you use the greater than or less than buttons on your keyboard, oops, sorry, I need to, hang on. If you use the greater than or less than buttons on your keyboard, it will move forward by 1 frame at a time, and each frame is a 30th of a second. So we're going to be working with time increments of 1/30th of a second. And we'll use the greater than or less than keys to do that. And then So to find distance, these are all 1 centimeter. So we can measure how far they go by just like seeing where it is at any one point and then clicking to see where it is at some later point. Okay, so but there's another trick to this too, which is that if we think about the kinds of systems that we're going to be working with in general, momentum is going to be conserved in the moments of time right around the collision. So typically what I try to do when I'm evaluating these things is I try to look at their velocity just before they come into contact. So I might think about like using 5 or 6 clicks. So like I did this earlier, so I kind of know where it is. This is at about 75 right here. And if I do 1, 2, 3, 4, 5 clicks, it's moving this way the whole time. It's an air track, so we can assume that it's moving at a constant speed. And that means we can use that 5 clicks and the distance that it moved to determine its velocity. Average velocity is what we're going to be finding. We're going to assume that there's very little acceleration over this time period. There's a couple other things to think about. The first is, the goal here, big goal is, can you get the relevant information? We need to know how fast something is going. To deal with momentum, we've got to be able to find velocities before and after collisions. This is one of the best ways to do it. Second piece to think about is we have, as one of our skills that we tabled from first semester, evaluating empirical data. You're all going to get different velocities. You're going to find that the numbers that you get are different because you're going to measure slightly different. Some of you are going to look at this and be like, well, that's exactly 63. Others of you are going to look at this and be like, well, it's a little bit to the left, so it's 62.8. Some of you are going to look at different sections of time. You're not all going to look at the exact same sections of time. You're going to get different numbers. How do you deal with that? How do you deal with the fact that the 30 students in here, we're going to get at least 20 different velocities? The second thing to think about is, how else could we find this? Like, this is a great way to find it, pretty quick, pretty easy, but you have another tool that you could use, which is Tracker. And I haven't done it yet. But one of the things that I want to emphasize to all of you is how kind of cool it is to think about stuff. Like, for example, when I did this, the last time I did this, we didn't have Tracker. It wasn't as easy to get videos in and out of the old program. But I'm super curious to know how close Tracker is going to be to the manual calculations that we make. You know, the frame rate, we can find distances. Tracker can do the same thing. So some of you are going to get this super fast and see what you can do with Tracker. Okay. So your goal by the end of the period is to have 4 velocities. Before and after for this cart, before and after for this cart. Let's just call this one the left cart. Let's call this one the right cart. We'll deal with variables, mass, and calculations tomorrow. All right? Any questions before you get started? All right, go to it.